think in slots of about 15 minutes, including questions. And the first speaker will be Daniel, who was already present at the last academic conference with a talk and a poster, so it's great to have you back again. And he will talk about pressure regularity for weak solutions of the Euler equations in the presence of boundaries.
So I will speak about the regularity of the pressure for weak solutions of in the incompressible Euler equations. And what I will say is joint work with Claude Bardos and Idris Titi. So the problem we consider is, as I said, the Euler equation. So suppose you have a fluid with a velocity field which depends both on space and time, and you have a pressure which also depends on space and time. I have a momentum balance where I ignore the viscosity effects, and I have conservation of mass with constant density, which is encoded in the divergence-free condition. So this equation is commonly solved by you first project this equation onto the divergence-free vector field, so you get the pressure gradient vanishes, and then you can solve this equation in some cases. And then later, once you have found the velocity field, you can recover the pressure via this Poisson-type equation, which you can obtain by taking the divergence of the Euler equations. So the problem we want to consider is, suppose I am given a velocity field which solves the Euler equations with a given regularity. What regularity does the pressure have? So, and we are specifically interested in the problem when you have a boundary. So when you have a fluid and it interacts with a boundary, and in this case we assume that we have a no normal flow boundary condition, so the velocity can only be tangential to the boundary. And the specific problem is, suppose the velocity field is Hölder continuous with exponent alpha, what regularity does the pressure have? And the reason this problem is phrased in the context of Hölder spaces is that they play a fundamental role in the theory of turbulence, because there's a connection between the exponent and the fact whether the weak solutions of Euler conserve energy or not. So in the presence of boundaries, we have to derive a boundary condition for the pressure, and in this case, we are considering this particular boundary condition. So n is the normal vector to the boundary, and so we have this Neumann-type boundary condition. And notice that if u is Hölder continuous with exponent more than 1/2, this term vanishes, and then you get the classical boundary condition, just dnp equals u cos u dotted with gradient of n. But we are interested in the low, also interested in the low regularity setting, so this in general will not hold. So the problem is, suppose I have this equation for given u, and I want to solve for p with this boundary condition. What regularity does the pressure have? So just to mention a few works before this, so this is related to the so-called Onsager conjecture, which I don't have time to mention, but it relates the regularity of the velocity field to the fact whether it conserves energy or not. And there are a lot of works about this which I'm skipping. I'm only discussing the works in the presence of boundaries, so Euler in a bounded domain. So first there was a work by Robinson, Rodrigo, and Skipper where they proved a sufficient condition for energy conservation in the half plane. And then later there were two works, first by Dos and Titi and then later with Wiedemann, where they proved a sufficient condition for weak solutions of Euler to conserve energy in general, C2 bounded domains, first with regularity on all of the domain and then later with only interior regularity. So this is related to turbulence, and I don't have time to talk about it, but just this problem on its own. So if I look at this equation for given u, what regularity does p have? That has also been considered by several people. So first, there were the works of Silvestri and Constantine, which are both on the whole space, and they proved that if u is C alpha, then p is C2 alpha. Then this was done later by Colombo, De Rosa, and Forcella, where they did this in the context of Bessel spaces. And then in the case where you have a boundary, there were the works of both by Dos and Titi and De Rosa, Latocca, and Stefani. So the theorem that we can prove is the following. So suppose I have a bounded domain with C2 boundary, and I'm given a velocity field which is L3 in time, but the time regularity is not of fundamental importance, and I have Hölder continuity alpha in space. And I assume that the velocity field solves the no normal flow boundary condition. then there exists a unique pressure which has the same Holder exponent, which solves the equation, and it satisfies the following Neumann boundary condition. And notice that this part is now here, the normal derivative of u dot n squared. And this is an essential part of the boundary condition, because you want to find, what we in fact show is that the normal derivative of this quantity is continuous in a very weak norm as you approach the boundary. And this is only true for this sum and not for dnp on its own. And we can even illustrate that with an example, namely that if you look at dn u dot n squared on its own, we constructed an example of the following, which is a Weierstrass type flow. So these are both very oscillatory functions. And so if you look at a velocity field given by u1 and u2, you can show that this is Holder continuous with exponent alpha. It is incompressible, which you can just see if you differentiate term by term. And it satisfies the boundary condition on the half space. So I'm looking at y bigger or equal to 0. So when y equals 0, this term just vanishes. So indeed, this boundary condition is satisfied. And now you can show, in fact, that if you look at dy of u2 squared, this is not defined at all. It's not even a distribution. So you can show that if you look at this normal derivative, as you approach the boundary and you square this, there are resonant terms, let's say, that blow up as you take the derivative at the boundary. So what this means is that this quantity on its own is not an h-2, it's not an h-5 million, it's not even a distribution. And in fact, we prove that this sum at the boundary is an h-2. So in particular, the normal derivative of the pressure on its own does not make sense as a normal distribution. So it's really essential to work with this boundary condition. So just to conclude, what we proved is we proved this pressure regularity result, namely that the Holder continuity of the velocity field gives you a pressure. If a velocity field is Holder continuous, it will give you a pressure, a unique pressure, with the same Holder exponent. And this is necessary for proving energy conservation of weak solutions, because this fact was used in these two papers. So you can prove now this criterion that if you are sufficiently regular as a solution of Euler, you will conserve energy. For the regularity proof, it is necessary to introduce a weak formulation of the boundary condition. As I said, we have to really include this term to get this trace lemma, to get a continuity in a weak norm as you approach the boundary. And finally, we construct an example where the use of this formulation is essential, really, that this dn u dot n squared is not even a distribution for a particular example of a flow. So you really have to consider this Neumann boundary condition as a whole. This is all I had to say. Thank you for your attention.
Thank you, Daniel. Are there any questions? So how do you find the pressure P? Because in a way you have this explicit formula for it given U, but you have to solve them at the same time, I guess, right?
No, you are given U. So what you do is you are given U, and then so first what you do is you mollify U, then you get a smooth approximation of the pressure, and then you want to take this limit as the smoothing vanishes, and then if you have enough bounds, and then you can conclude that there is a pressure, let's say, and that it has this regularity. I mean, the point is the existence, not the uniqueness, because I can just, if I would have two solutions, I can subtract them, and then I have something that satisfies the Laplace equation, and then it must be.
So where do you get the uniqueness from?
I mean, if suppose I would have two, I subtract, so I have P1 minus P2, its Laplacian equals 0.
Yeah,
and I have
so where do you get uniqueness from, if it's not from this?
No, I said I get it from this. I just get it from subtracting. This is what I meant. I said the uniqueness is not the issue. I said the existence is.
Okay, sorry. Okay.
The existence is like you have to, when you do the approximation, you have to keep the regularity uniform in the approximation. This is the point.
I see. Okay. Great. Any more questions? Okay. off to a great start on the elevator. Thank you. So, who's the next one? Ah, perfect.